final minus initial.
Okay, you're right.
I'm right?
Yeah, you're right. You're right for the last one.
Okay,
Okay,
so
so which cases do energy flow out of the system? The system?
more so than any other
It's not negative.
You just said it was positive.
chapter
The work
in
is negative.
this study
The
of AP
pressure is when
chemistry,
it's negative pressure.
this is
No, it's
all
not.
about
It's
vocabulary,
negative
okay?
1 times.
Is volume getting bigger? Is volume getting smaller? Is work being done on the system? Is work being done by the system? Okay? So, I don't know.
You get 32.
So let's talk about number 3, for example. Okay?
Sure.
So the volume of an ideal gas is decreased from 5 liters to 1 liter. Okay? At constant pressure, 2 atmospheres, determine the work associated with this process. Okay? So that's like taking this, okay, and we're going to decrease the volume. Okay? So your work on number 3 is just going to be, work is going to equal negative P delta V. So right away, here's what you, and again, I don't care how you do this. So you got your pressure in atmospheres, so that's negative 2 atm. So your change in volume, this is vital that you realize it's final minus initial, okay? So you're going from 5 liters to 1 liter. So your final volume is going to be how much? 1 liter. Minus 5, okay? And then it's just a straight multiplication. So on number 3, in terms of units, if you leave it like this, which is cool in the physics class, this work is going to be, number 1 is going to be a positive or negative value.
Positive.
Positive. And you can leave it in atmosphere liters.
Let's
So
go.
chemistry is the only real science that you can talk about work in atmosphere liters. Now, for those of you that have had physics and you're flipping out going, oh my God, I can't talk about work in terms of atmosphere liters, there's a handy dandy conversion where you can convert that into joules. So if you look on the back of the lecture notes, there's a conversion between joules and atmosphere liters. It's 101.3. I don't care what you have your answer in. Just don't write down a number and think, oh, I'm going to know what units that is. I don't care. Pick one. But if you stick in atmosphere liters, your answer to number 3 should be around, I don't know, 8. It's an ish. If you work in joules, it's going to be around 800. Okay? Now, so here's the trend that you want to see. In this situation, work is done on a system, okay? So if you look at delta E, in physics we call it delta U. It's the same idea. This is the change, and this is going to be important. This isn't the energy, okay? This is the change in energy, okay? It is not the energy. It is the change in the energy, which is equal to Q plus W. Q is the thermal side, energy, thermal energy going in, thermal energy coming out, okay? Put it in an ice bath, put it in a hot water bath. That's going to be your Q value, okay? Take the thermometer and hold it in your hand, thermal energy. So here's the important part of this. If you look at what we just did, that's a positive value of work. So we haven't changed the thermal side of this. We didn't put it in an ice water bath and do this. All we did was just compress the gas. So here's, and again, do not, if you're really going to understand this, you cannot just say, hey, I'm just going to get a number and write it down. You have to understand why this works. So I don't have to worry about the Q value on this calculation because of the fact that there's no thermal energy. I do have to worry about the work side of it because there's a change in volume. So my delta E is going to be a positive number. This is why yesterday, when I rapidly compressed that gas, it ignited the cotton that was in there. because I had a rapid increase in the energy inside the system. And that's what caught that on fire, okay? Now, on the other side of it is that if I pull that syringe back and increase the volume, then my delta E is going to be a negative value. So what you're looking at is the energy that's happening inside. This is why, bam, I slammed that down, I ignited that cotton, okay? All right. Now, if you look at number 4. So number 4 is a little bit more complicated because the balloon is filled with 39.1 moles of helium, gave you the molar mass, 1 atmosphere of pressure, volume 876, temperature is increased by 38 Kelvin. As this volume expands to 998 under constant pressure, determine Q, W, and delta E for the process. Okay, so let's start with the Q part of this. So you all are used to having mass times change in temperature times specific heat, and specific heat being grams per, or joules per gram degree Celsius, okay? That's what that's in, joules per gram degree Celsius. But with this one, mainly because of the fact that with gases, like it's easy, sometimes it's just easier to measure volume and than it is to measure the mass of the gas inside the flask, which sounds like a Dr. Seuss line. So a lot of time with the gases, it'll be joules per mole degrees Celsius. It's the same concept, okay? The only difference is that this is how much energy it takes to change at 1 degree Celsius if you have 1 mole of it. This, what traditional specific heat is just based upon grams. It's the exact same idea. So, now, and this is going to be important in the lab today. So, in this situation, you're going to warm this thing up from 38 degrees. You're going to start at 273, it's increased by 38 Kelvin. As long as you're just talking about the change in temperature, whether it's change in Celsius, change in Kelvin, doesn't make any difference. It's the same value, okay? The numeric values of the temperature are different, but the change is still the same number. So, you can calculate the value of Q. So, your Q value in joules is going to be a decent GPA times 10 to the 4th. Yes?
Is it cool if I put it in kilojoules?
Yeah, you can put it in kilojoules, that's
Okay,
it.
thank you.
Okay? Just as long as you let me know what it is. Now, the work side of this, okay? So by this point, you should be able to read a question and right away, before you do any calculations, know what the sign of your work is going to be. So, you're at 876, the temperature is increased by 38, the volume expands to 998. So the volume's getting bigger, okay? So since the volume is getting bigger, what's going to be the sign of your work value?
Negative.
It's going to be a negative value. So here's what's happening, okay, if you're a visual kind of person. So we're heating this thing up, and at the same time, what you would physically see is that you would see this plunger or you would see the balloon getting bigger, okay? So what's happening is that you're taking that energy and you're taking some of that energy and you're using it to do work. It would be like, upon my passing, in my will, I am going to leave to 1G $100,000.
Let's go.
Okay? 1,000 Gs. Okay? You're going to get that money. But the caveat is that you have to take 40,000 of that and do work with it. You have to make the world a better place.
There he is.
Hey, Berg, I have an I'm sorry cupcake. Here. It's like a passport cupcake.
Berg, I would ask where that's from.
Yeah, where is that from?
Oh, the choir.
Oh, great.
Choir kid germs on it.
Jazz hand. Okay.
Are there choir cookies on it?
I don't know.
It's been hampered by jazz hands. Great. Okay. So she's gonna be able to keep $60,000 of it. Okay? That's gonna go to increase her bank account. But she can't keep all of it. You can keep a large portion of it, maybe buy canning bits. Okay?
Yes.
There you go. Woo!
Good.
Bye. Oh, you're in-home
Let's
cancer.
go, Villanova.
You're in-home cancer factory.
Let's
Cool.
go.
Yay. So, what's happening is that you have two divergent ideas on number 4. You have energy going in, so if you look at delta E equaling Q plus W, you have two divergent ideas. Energy is going in, but at the same time you're increasing the volume. So you're taking some of that energy, that thermal energy that you're putting in, and you're taking some of it to do work to make the volume bigger, okay? Now, this is where you have to pay attention to the units. So you have negative P delta V, okay? So the work side of this, in the units that you have, is going to be in atmosphere liters. Your Q calculation is going to be in joules. You cannot add atmosphere liters to joules, okay? Can't happen. So you need to make a decision, and I care not what, okay? Then you either need to change the atmosphere liters into joules or change the joules into atmosphere liters. It's a personal preference thing. But if all goes well, if your delta E value, if you are in kilojoules, should be around your current age.
Okay. I'm okay.
Okay? If you're around it should be around your current age in kilojoules. Now, so I can be 1G's best friend. Let's talk about number 5. Okay? So,
High stakes.
high stakes.
I know.
I can't screw this
The
up.
exact same number, just have different signs, yeah.
No, it was so I could be your best friend, not so you could be mine.
Oh, my bad.
Yeah.
Wow.
That was harsh.
Use A and B?
No, I'm lying. You're my best friend.
No, whatever.
It's because you're already her best
What do you
friend.
have?
Yeah, exactly.
We're just maintaining that status.
No, like
Well-
I'm making sure that I'm your best friend, but you're already my best
I
friend.
have
So that's
A
not
and
like
B
even
on
a
We're just trying to
A and C on-
reciprocate this.
Exactly.
Yeah.
Okay. This is complicated.
I don't
Okay.
think so.
I think.
I don't
All right. So you have to understand what this means.
That was where I went wrong.
A.
So this negative 296 kilojoules per mole, start with this idea. Is this reaction endothermic or exothermic?
A and C.
Exothermic, how do you know? This is one of the certain things you have to know without hesitation. I mean, like, no thought whatsoever. The first thing that you need to learn right from the get-go is that if you have negative delta H, that's an exothermic reaction. You have a positive delta H, that's an endothermic reaction. That knowledge has to be, without hesitation, boom, got it, okay? Tattoo it on your best friend's forehead so you can look at that and remember it,
Oh,
okay?
we're getting matching tattoos.
I'm gonna hold the hair
Yeah.
and see it.
No, that'd be weird, okay? Negative delta H equals exo?
You think?
Oh, it would just be weird.
I don't think it would be weird.
I think the
You
tattoo.
be best friend
so-
matching tattoos. That's not weird.
On our foreheads, really?
Yes.
Okay, anyway,
That's the
Get it after
tattoo.
graduation.
so,
I wanna be there.
okay. Now, so what this means, and this is what's different from your values on your reduction chart. Remember back on the reduction chart, like for example, silver Ag plus 1 electron equals Ag, that had a value positive 0.80 volts, okay?
Yeah.
That was the same whether or not I had, you know, a little bit of
Bless you.
silver or I had a big chunk of silver. Because that's what's known as an intrinsic property. The amount of silver that I had didn't matter. It's still 0.80 volts. Because there was no, like, if you look at that volts, that was just volts. It wasn't volts per mole. It was just straight up volts. So if I multiplied stuff by 5 to get 5 electrons to balance stuff out, I did not multiply the 0.8 by 5 because it was an intrinsic property. Doesn't matter. Your thermo properties are all going to be per mole. So what that means is, like, if you double the number of moles, like this is, let's call this negative 300. This is negative 300 kilojoules per mole. So that's, in this situation, everything on here has a coefficient of 1, okay? So what this would look like, anybody happen to know the color of elemental sulfur?
Yellow, right?
Yeah, it's like a yellow powder. You burn that in pure oxygen, you're gonna make sulfur dioxide, okay? Just like if you burn carbon, you make carbon dioxide. You burn sulfur, you get sulfur dioxide. So now, interesting thing happens. You're gonna take sulfur and you're gonna burn it in oxygen. What's gonna happen to the mass of sulfur in the weighing dish when you burn this? It's gonna go down because of the fact that sulfur is being changed into sulfur dioxide as a gas. Okay. Now, if this had been a solid, the mass would actually increase. So like if you burn iron in oxygen, you get iron oxide. That's a solid. So that in that situation, you would actually see the mass on the weighing dish increase because you're making iron oxide, which is a solid. This one, you would see the sulfur actually decrease in mass because you're making a gas of sulfur dioxide. So, because everything is a 1, what that means is that you have negative 296 per 1 mole of sulfur dioxide per 1 mole of oxygen or per 1 mole of sulfur. Now, if there had been, let's just say a 3 in front of the oxygen, there isn't, but let's just say there was. What that would mean is that you would evolve 296 kilojoules per 3 moles of oxygen, or per 1 mole of sulfur dioxide, or per 1 mole of sulfur. Later on, we're going to get into what's called enthalpy of formation. So when you do thermo equations, typically you want the lowest coefficient to be a value of 1. So sometimes when you see thermo equations, you'll see fractions, which seems really, really weird, like a half of an oxygen molecule, like you'll see a 1/2 in front of there. All we're doing that is so that way we have that thermodynamic value per 1 mole of a product, okay? So if you see fractions, so for that, Mr. Burkamp, we were told we can never have fractions. Well, you hadn't studied thermodynamics at that point in your life, and now you have. So here's what you're gonna do on A. You got 275 grams of sulfur. What's the first thing you need to do with the grams of sulfur? Convert that into moles. Molar mass of sulfur is?
32.06 grams.
So I'll call it 32.1 grams per 1 mole of sulfur. That's per 1 mole of sulfur. Now, your number here is that you have 296 kilojoules per 1 mole of sulfur. Grams of sulfur cancel out, moles of sulfur cancel out. So your answer to like 5A would make an GPA times 10 to the 3rd kilojoules.
That's positive or negative?
In this situation, because it's always asking for how much heat is evolved, it's just like an absolute value.
Okay.
Because they're always asking for is heat.
Would you count us wrong if it's negative?
No.
Okay.
Wait, would you say the answer was like an GPA?
So we're both.
An okay GPA, not really, it's kind of a bad
It's a
GPA,
bad G.
times 10 to the 3rd,
Third?
in kilojoules.
Oh, in kilojoules. Yes. Okay, thank you. We're best friends now.
Okay, looked at it.
5B is also times 10 to the 3rd.
Yeah, I thought it.
5C is around 700.
Okay.
B is more than a GPA, right?
Huh?
Like B is more than a GPA?
Like it's
B
not
is-
possible to get that
Yeah,
GPA?
it's not
Okay,
possible.
Okay, good.
Well, I like to hear.
That'd be a crazy weight system.
Yeah.
Yeah, what kind of classes would those?
Okay, it would make a good earthquake, how about that?
Yeah,
Okay, yeah.
Like that?
Yeah.
Start going by Greek letters, like take,
Okay,
get a
now-
sigma and an AP class.
Let's talk about number 8, because number 8 is what you're gonna do in the lab today, so I wanna make sure everybody, huh?
You started giggling.
Charles is making jokes, we're laughing, it's cool.
I'm hilarious. Haven't said a singular word yet in Charles' autistic.
Glad you told me.
See? Brought you rolling around.
How many of them are negative?
On what?
Do you think? What?
Oh, no. Oh, there are negative answers.
Okay, well.
Oh, no, they're not. Okay, so let's talk about number 8, because this is, bless you, exactly the calculations you have to do in the lab today. Okay? So I want to make sure everybody's cool with this. And it's literally called coffee cup calorimetry. So you're, like in the lab, you're going to have 2 styrofoam cups stacked together. Leave them stacked, okay? The reason that we have that, don't separate them out. Oh, look, I have 2 cups. Leave them stacked. Because what you're trying to do is minimize any thermal loss or gain from the outside environment. Okay? That's why it's called coffee cup calorimetry. And we use styrofoam because styrofoam basically is a lot of dead airspace, and the thermal transfer is very difficult to do through that process. Okay? That's the whole point. So, you're going to have 75 grams of water. Okay? Initial temperature is 25.00 degrees Celsius. And you're going to basically take that 1.6 grams of ammonium nitrate, dissolve it in there, and then afterwards, the temperature drops to 23.34 degrees Celsius. Okay? Now, this is going to be important. Listen to me. And this is what you're going to see in the lab. You're going to run 2 different experiments. In one of them, the temperature should drop. Okay? Again, you're going to have a thermometer in here. When you measure the temperature of the water, are you measuring the system or are you measuring the surroundings?
Surroundings.
You are keeping track of what's happening in the surroundings. It's not the system. Okay? This is vital. So the water is the surroundings. Okay? It's not the system. We can't observe the system, but we figure out what's happening in the surroundings. It would be like someone's teaching next door to me, and they hear you guys starting to laugh and all this good stuff. They go, oh yeah, we don't know what's going on, but we hear laughter. Hey, you guys are having a good time in there. Versus, oh, there's wailing and gnashing teeth. We go, oh my God, Bergkamp's giving a test. It's bad. Okay? So,
That's not you giving the test, that's you giving back the test.
okay. But anyway, so here's the point. They can't observe directly what's going on, but they observe the impact that that has, and then they figure out what took place. Now, listen to me.
No.
You're going to use Q equals M delta T C sub P. Now, this is the change in temperature of the surroundings. The mass has to be the mass of the water and the mass of the ammonium nitrate. You guys are going to be using copper sulfate. Okay? You add that to it because it's dissolving and it's becoming part of the water. If it was a chunk of metal, you wouldn't add in the metal in there to the water. It would just be the water. But since it's dissolving, and since it's become part of the water itself, you add the mass of the ammonium nitrate. So that's going to be like 76.6.
Yeah.
Okay. Now, your change in temperature. Is your change in temperature going to be a positive or negative value?
Negative.
Negative. So we'll have a change in temperature because the temperature went down. The specific heat of water, 4.18 joules per gram degrees Celsius. So is your Q for the surroundings, going to be a positive or negative number?
Negative.
Negative number. So Q surroundings is going to be a negative number. Bless you. Okay? So if that's Q, if you have a negative Q for the surroundings, that energy got lost. Where did the energy go?
The system.
Into the system. So Q for the system is going to have the exact same numeric value, but you make it
Positive.
positive.
Yes, yes.
Okay? So I'm going to have a positive Q for the system. Now, your delta H is going to equal the system divided by the moles of whatever you have. Okay? So your Q value should be around 530. Okay, joules. So your value for Q should be around 530. Then you've got the 1.6 grams of ammonium nitrate. What are you going to have to do with grams of ammonium nitrate?
Convert to moles.
Convert that into moles. So then you're going to take that Q value of around 530 joules, which is positive, and then you're going to divide that by the moles of the ammonium nitrate, not the moles of the water. The water is not the system. You're looking at the ammonium nitrate part of this. So if you do this in kilojoules, okay, kilojoules per mole, you should get around 25 kilojoules per mole as your answer to number 8.
I'm okay with that.
Okay? Now, here's this is why it is so vital that you switch the signs. So as soon as you see that positive delta H, endothermic, exothermic,
Endo.
endo, because of the fact that this is why the temperature went down.
Okay, so that makes
Okay? Right?
It tracks.
sense.
So, now again, don't try and think too much about the actual mechanism that is happening. Okay, so remember, you have a thermometer, and this is what you do in lab day. You're going to have a thermometer. Thermometer is like a speed gun. It measures how fast the particles are moving. So in this situation, somehow or another, when you put that ammonium nitrate in there, those water particles slowed down. Okay? Something made them move slower. That's why the temperature dropped. Okay? Now, when you get to number 9, okay? On number 9, is it endothermic or exothermic?
Let me reread the question.
Number 9, endo or exo?
Exo.
Exo, how do you know?
Negative.
Got a negative delta H, right? Okay. So you got 11 grams calcium chloride dissolved in 125 grams of water, both at 25 degrees Celsius. Calculate the final temperature of the solution. Now, let's just think this through. Before you do any math at all on number 9, you're starting at 25 degrees Celsius.
Okay.
It's an exothermic reaction.
Okay.
So does your final answer have to be bigger or smaller than 25 degrees?
Bigger.
Bigger. So if you have an answer less than 25 degrees, you have violated the laws of thermodynamics. Congratulations. Yay! Bad. Now, here's what you're going to do. There's a couple of steps you have to do on number 9. First off, what are you going to do with 11 grams of calcium chloride?
Convert to moles. of calcium.
Convert that into moles. Now, your delta H value is 81.5 kilojoules per mole. So if I multiply that by moles, and this is where you have to pay attention to the units. You're going to take the 81.5, multiply it by moles. If you do that, what units is your energy going to be in? That's going to be in kilojoules, okay? And that's cool. But here's the problem. First off, when you're doing the Q calculation and you're going to do M temperature minus temperature final, or T minus T naught, temperature final minus initial, I don't care, times the specific heat, right? What are you solving for, the final temperature or the initial temperature?
Final.
Final. But here's the story. This Q is for the surroundings. So you have a negative delta H. But when you put it in for the Q value, what do you have to do?
Positive.
Make it positive. Okay? You have to make it a positive value. So then it turns into an algebra problem. How are you going to get that final temperature by itself? So your answer to number 9 should involve a 9.
Okay.
No, Celsius.
Uh-oh. Oh,
don't like.
9 Kelvin.
Okay, wait.
Maybe
Okay,
it's not 9.
should our, when we convert from kilojoules per mole to just kilojoules, should it be
I don't
negative or
quite know what I
positive?
did.
That should
I
be a
did this last
positive
night when I
value
was-
because you're talking about Q for the surroundings. So,
Yeah, you got it, you got it.
yeah, so your Q value should be around 8,000 joules,
Okay, that's good.
okay? And then it just turns, so this is around 8,000, but that's a positive number, okay? So then it's just an algebra problem. How do you get that final temperature by itself? So this is why, again, when you look at the big picture, the only way you can get a positive value for Q is if that final temperature is bigger than the initial temperature. If it's not, you're screwed algebraically right from the get-go.
Somewhere you messed up.
Yeah. On number, let's see, what did we talk about? On number 6, that answer to 6A, in joules, should be around 5 times 10 to the 4th. Okay, that's in joules. On that 6B, you want to change, the only thing difference is that you're changing it from joules per gram into joules per mole. It's just a matter of making the stoich work out. Your answer to 6B is in joules per mole, should be in the mid-20s.
So it's just joules per mole.
You don't
Degrees
need-
Celsius.
I had, okay.
Degrees Celsius. How would you? Because I have. Say, can you say that again? Around what?
Mid-20s.
Mid-20s.
Joules per mole.
I have
degree
that, but I only have joules. I solved
shouldn't call
it
me
out for
joules.
joules.
But it's, but your specific heat
by mole
is joules per gram degree Celsius. You're keeping everything, you're just changing the grams to moles. Does that make sense? So on number 6, okay, you have 0.9 joules per gram degree Celsius.
Yeah, I have that. Yeah.
All you're changing it is from joules per gram degree Celsius to joules per mole degree Celsius.
Well, I guess you could. Because I have that. I have
On
the.
6B,
Yeah, 6B. Yeah, I have that. I have the. Then what? Where would the degree Celsius?
The change in temperature.
do you agree that it's joules per gram degree Celsius?
If you say so.
It says it on the paper on number 6. It says that the specific heat capacity is 0.9 joules per gram degree Celsius.
Yeah.
Okay? Molar heat capacity, which means we're going to change it to 1 mole. So the only thing that happens is that we're going to get rid of the grams and we're going to get moles down here. The degree Celsius stays there because you're not doing anything to change the degree Celsius.
So I just wouldn't. Okay. Never mind.
The number is right, Charles.
I know-
Just
I
write
know
joules
the
per
number's
mole
right. I
degree
don't know
Celsius
why
by
you-
it.
Why you do it like that?
The number is right. Just write joules per mole degree Celsius.
So annoying. Okay, anyway.
4 more weeks of this.
Believe me, I've got a calendar.
I do believe.
Okay.
Start off every day.
100%.
Minute. All right. Kidding. All right.
That's your best friend.
No, but because I'm gonna be sad once I cherish every night.
Oh, yeah, of course. That's how that works.
All right, anything else? Once, twice, what?
Okay. And I asked this only because I was checking answers before class with like 4 people and got 3 different combinations of answers. Can you like give a little hint on D and E of 1? 1, D, and E.
In which case does the energy flow out of the system? There's only one situation where the energy flows out of the system.
Okay.
Okay.
What about you?
Okay?
Okay.
there's two answers on E.
Okay, how is there only one where it flows out of the system? Because if it flows out of the system, that'd be a negative delta H, so wouldn't it be a
No,
positive
no,
Q?
no. Q is the only thing that determines your heat flow.
Okay.
Don't confuse, this is not delta H, this is just Q.
Okay.
This is just Q, that's it.
Okay.
You can find Q, use Q to find delta H, but that isn't the point of the story,
Okay.
okay? You're making this complicated. Don't,
Okay.
okay? All right,
Wait, no, because it's. How is it?
this is not this difficult,
Speak for
E.
yourself, Roxanne.
huh?
Give us a hint on E.
It said two.
Shut up. Shut up, gum.
Should each letter be used once?
Work equals negative P delta V, right?
Yes.
Okay. In which case does the system do work on the surroundings? If it does work on the surroundings, is the volume getting bigger or is the volume getting smaller?
Bigger.
Volume's getting bigger, which means that your delta V value is going to be a
Negative number.
Positive.
Positive number.
positive. The volume is getting bigger, right?
Yes.
Yeah, dude.
So if you have a positive delta V times a negative value of pressure, what's going to be the sign of your work?
Negative.
Negative.
So work is only done on the surroundings if work has a positive or negative sign.
Negative. So should we have one letter not used at all?
Yes.
Okay. We're good.
Wait, what?
One of the letters is not used at all on your answers on D and E.
And one is used twice.
Yeah.
Yes, that is how that works.
We're good.
What?
We're good. No.
Would it be the start of my name?
It might be the start of your name. I got the start
Does
of
it
your
start
name.
with a,
Twice.
is it a letter that minions really like? That, no.